All right, this is MA 161's exam 3 from spring 2022. So let's get started. Question 1, the graph of the velocity function of a particle is shown below. On what intervals do the velocity and the acceleration have opposite signs? Okay, so signs of velocity acceleration, since we're given the velocity function, it's pretty easy to tell when the velocity is positive or negative. It's just going to be when it's in the top half or the bottom half. So I'm going to color code this a little bit. I'm going to use some shades of red and green to illustrate this. So I'm going to use this kind of purple color whenever the velocity is positive, and I'll do a lime green when it's negative. So I said when the velocity is positive, it's just in the top half of the graph. So I'm going to shade the top half of the graph in this purple. And then on the bottom half, I'll do this green whenever the graph is negative. So that is our velocity. And now for acceleration, since acceleration is just the derivative of the velocity, we can just look at the slope of the velocity to determine the sign of the acceleration. So I'm going to use red for when the acceleration is positive, whenever the slope is positive. So that's segments like right here. When the slope is increasing, it's positive. It looks like that. It's going to stop there at that peak, since after that, it's going to have a negative slope. But it's going to pick back up and have another positive slope at the end here as it approaches infinity. And then in between those 2 points, we've got a negative slope. I'm going to do that in this different colored green. And we've successfully color-coded our graph for the signs of velocity and acceleration. So now that we have this, we can sort of inspect it and determine our answer. So since it asked for when the velocity and the acceleration have opposite signs, we just look for whenever there's sort of a red color matched up with a green color, since that means we have a positive and a negative at the same time. So it looks like one of those intervals is going to be right here. Looks like we've got a positive velocity and a negative acceleration. So we've got something like that there. Looks like we've also got another one down here. It's the opposite case. We've got a negative velocity and a positive acceleration. So these two intervals, looks like the bottom one is maybe 0 to 1. And then we've got the top one that looks like it's from 2 to 4. So our answer is E. Question 2, this is just a derivative question. We've got our f of x here. It's ln of x, the quantity raised to the power of x. And we have to take its derivative and then plug in e. Awesome. So for this derivative, unfortunately, we're kind of inclined to do the power rule here since we've got a power to start off with. But that won't work because our power is an x. It's not a constant. The power rule only works if it's like squared or cubed or something like that, not when the power is x. So for this problem, we're going to use the generalized power rule. So that states if you have something in the form of a to the power of b, and you want to take its derivative, that's equal to, let's see, this will be a to the power of b times the derivative of b times ln of a. So that is the generalized power rule. In this case, our a is ln of x, and our b is x. So we just fit those to this formula, and we'll get our derivative. So we've got f prime of x. That'll equal the same thing rewritten, which is ln of x to the power of x, times the derivative of b, which is x, times ln of a. So that's going to be ln of a. And that is the derivative. Cool. So now we'll go ahead and find the derivative of this. X times ln of a. That is going to, since we have two things being multiplied together, we should probably do the product rule there. That states you have something in the form of a times b, and you want to take its derivative. That's equal to a prime b plus ab prime. In this case, our a is x, and our b is ln of a. So we just fit those to this new formula and get our inside derivative. So this equals ln of x to the power of x times, all right, so a prime, that is derivative of x, that's going to be 1, times b, that's ln ln of x. Why did I write an a up here? That's weird. Ln of x plus a, which is x, times b prime. That is the derivative of ln of x. That is going to be an additional inside derivative that we have to do. So I'm going to split this off into another step that we'll do down below. I'll just do ln of x prime here and then call it a day for this step. So next step, we've got ln of x to the power of x times 1 times ln of x plus x times, all right, derivative of ln of x. So derivative of ln, that is just going to be 1 over the inside. The inside is that, so it's going to be 1 over ln of x. But we have to do chain rule here. We have to multiply by the derivative of the inside. And the derivative of ln of x, again, is just 1 over x. So it's going to be 1 over ln of x times 1 over x for that inside derivative. And then after that, we now have our full f prime of x. So now that we have that, we can go ahead and plug in e. We can find f prime of e. So plugging in e, we get ln of e to the power of e times 1 times ln of e plus e times 1 over ln of e times 1 over e. All right, now simplifying this is just going to be 1 because ln of e is 1, and 1 to the power of e is also 1. So it's going to be 1 times, so this 1 isn't going to do anything, and this ln of e, so ln of e is 1 and ln of 1 is 0, so it's going to be 0 plus, and then we've got this, so e times 1 over ln of e times 1 over e. That's just going to be 1 over e times ln of e. Cool. Let's go one step further. This is going to be, so this 1 times is not going to do anything, and this 0 plus is not going to do anything. This is just going to be e times 1 over e to the ln of e. This e and this e are going to cancel each other out. This is now just 1 over ln of e. Ln of e is just 1, so we're left with 1. Answer choice A. Question 3. All right, this is another derivative question. We've got our f of x equals ln of sine of x squared, and we have to find its derivative. Don't even have to plug in a value afterwards. So first thing we do for this derivative, looks like it's an ln, so we take the derivative of ln. That is just 1 over the inside, so this is going to be 1 over the inside, which is sine of x squared. Now we do have to do chain rule. We have to multiply by the derivative of the inside. That was sine of x squared, so we multiply by the derivative of sine of x squared. So doing that, we get 1 over sine of x squared times, so derivative of sine is just cosine, so that's going to be cosine of x squared. But we do have to multiply, again, we have to do chain rule, multiply by the derivative of the inside. Derivative of x squared is just going to be 2x. So that should be our derivative, actually. It just wants it in a different form, I guess. There's a lot of cotangents in our answer choices. Oh, okay, that's how they got it. So there's a cosine over here and a sine down there. So I guess it combines them into just a cotangent. So that's going to be cotangent of x squared, actually. Whoops. Of x squared times 2x. Yeah, that's it. Answer choice D. Awesome. Question 4. This is related rates. So the area of a right triangle is increasing at a rate of 2 meters squared per second. I almost just said meters per second squared as if this was like a physics problem. If the 2 legs of the triangle are increasing at the same constant rate, how fast are the lengths of the legs increasing at the moment when each leg is 5 meters long? All right, so let's draw this out. That usually makes these a lot easier. So we've got a right triangle, and the 2 legs are they're the same length and they increase at the same length. So at the moment we're looking for, they're both 5 meters long, and they are also increasing at the same rate, and that is actually our unknown our answer. That's what we're looking for. So we've got that. We've also got our area on the inside. That is increasing at a rate of 2 meters squared per second. So dA over dt equals 2. And that is everything that it gives us. So first thing you do for related rates after you draw it out is determine what formula you should use that relates a lot of these pieces of information that we're given together. So since we're given a lot of side lengths and we have to relate it to area, we should probably just use the area formula of a right triangle. That goes, the area equals 1/2 times the lengths of the two legs, A times B. But the cool thing for this problem is that the lengths of the legs are always the same and they increase at the same rate. So you can really just combine them into the same length and do something like b squared, b times b. So now that we have our formula, we can go ahead and take its derivative. So on the left, we're going to have dA over dt. And on the right, we do power rule, put the 2 out front. That's going to become 2 times 1/2, which is just 1. So we're left with just b times dB over dt. Cool. So now we can go ahead and plug in the information that we know. We're given dA over dt, that's 2 meters squared per second. We are also given dB over dt. We're trying to find dB over dt, the rate at which the lengths of the legs are increasing. We're given b, which is 5 meters at that given point. So we go ahead and plug those numbers in. We get 2 equals 5 times dB over dt. Divide both sides by 5. You get 2/5 as our answer. So our answer is answer choice A. That is, the lengths of the legs are increasing at a rate of 2/5 meters per second at the moment when each leg is 5 meters long. Question 6. Use a linear approximation to estimate the value of square root of 36 plus 3. All right, so linear approximation, how these goes, you've got your linear approximation formula. So f of x approximately equals f of a plus f prime of a times x minus a. So in this case, we need 4 pieces of information. Those 4 are x, a, f of x, and f prime of x. Those are the 4 things you need to do this problem. First, let's find f of x. I know it's the third thing I put here, but it's easier if we find that first. That's just the original expression you're given, but with an x in place of the decimal that you're given. So this is going to be square root of x. Now let's do f prime of x. So if f of x, this is just equal to x to the power of 1/2. So f prime of x, we can just do power rule and put that 1/2 out front. This is going to be 1/2 x to the negative 1/2 power. And now this is just equal to 1 over 2 times x to the positive 1/2, which is just square root of x. So that's our f prime of x. And now to find x and a, well, x is just the original decimal. That's just 36.3. And our a, that is our approximated value. So a is a value that's going to be really close to x, but is a lot easier to go ahead and solve your expression for. So since 36 is both really close to 36.3 and is also way easier to take the square root of, square root of 36 is just 6. You can do that in your mind. We're going to put a equals 36. So those are our 4 pieces of information we need for a linear approximation. We can go ahead and use all of those to fill out this formula and get our answer. So this is approximately equal to f of a. That's going to be the square root of 36. Now we've got plus f prime of a. That's going to be 1 over 2 times the square root of 36. This is all times x minus a. So this is going to be 36.3 minus 36. So simplifying now, we'll get approximately equal to 6 plus, so 1 over 2 times square root of 36. So square root of 36 is 6. 2 times 6 is 12. So this is 1/12 times 36.3 minus 36. That is 0.3. Now combining a fraction and a decimal, that's not very fun, but doing that anyways, we get 6 plus well, 0.3, that can be rewritten as 3/10. So this is the same as 3 over 120. We can go ahead and simplify this even further. We have a common common factor in both the numerator and the denominator. This becomes 6 plus a 40th. Now a 40th, converting that to a decimal, I'm pretty sure is 0.025, because if you multiply this by 4, that equals 0.1, and that times 10 is 1. So it's 4 times 10 is 40. So this is the same as 6.025 is our answer. So we've got answer choice B. Question 7. Find the absolute maximum and minimum values of the function f of x equals x to the 8/3 power on the interval from -1 to 8. Okay, so we need to find maximums and minimums, and to do that, we need to find f of x's critical points. And to find those, we set 0 equal to f prime of x, and then solve for x after we do that. So first we need to find f prime of x, the derivative of x to the 8/3 power. And to do that, we just do power rule, move the 8/3 out front, subtract it by 1. So that gives us, let me give myself a little more room. So that'll be 0 equals 8/3 times x to the 5/3 power. Now solving for 0, we can divide both sides by 8/3. That'll give us x to the 5/3 power. We can rewrite x to the 5/3 as the cubed root of x to the 5th. Now we can cube both sides to get rid of the cubed root. So 0 equals x to the 5th. Now we can 5th root both sides to get rid of the power of 5. So we get 0 equals x. So that is our one and only critical point for f of x. But we do also have to worry about the points -1 and 8, since this is just an interval. So those endpoints could very well be a maximum and a minimum, just only among that interval. So setting up that table again, we've got x and f of x. We've got our 3 values that we have to worry about in ascending order. They're -1, 0, and 8. And then plugging them into the original function would be hard unless we rewrote it as the cubed root of x to the 8th. Actually, let's do it the other way around. That would probably be even easier. Let's do the cubed root of x to the 8th power. That would work as well. So, all right. So -1, the cubed root of -1 is just -1, and 1 to the 8th power, or -1 to the 8th power, is 1. Cubed root of 0 is 0, and 0 to the 8th is also 0. And whoops, I just erased stuff. That's supposed to be a 0. Cool. Cubed root of 8 is 2, and 2 to the 8th power is, let's see, 2, 4, 8, 16, 32, 64, 128, 256. So that is the 8th root, or the 2 to the 8th power. Now we're asked to find the max and min, so it looks like this is our max and this is our min, so our answer choice is D. Question 8. Determine whether Rolle's theorem applies to the function f of x equals negative sine of 4x on the interval from pi over 4 to pi over 2. If so, find the x values where horizontal tangent lines are guaranteed to exist. All right, so Rolle's theorem, what it needs to work is for whatever interval you give, it needs to be differentiable and continuous for every value within that interval. And fortunately, the sine function it's just a big wave. It's always differentiable and it's always continuous. There's no holes and there's no vertical asymptotes. So for our function that we're given, it does apply, so that means A and B are out. And the cool thing is, if you look closely at answer choices C through E, you can also rule out D and E, because look at what it is saying at the end of them. So it's saying that Rolle's theorem applies in a horizontal tangent line is guaranteed to exist at x equals pi over 6, and in this case also x equals 3 pi over 8. But these two can't really happen because pi over 6 is outside of the interval that we've defined. So D and E don't really apply to this problem. They're thrown out, and we're left with answer choice C as our answer. Question 9. Find the values of C that satisfy the equation. And this is just the mean value theorem. This is just f of b minus f of a all over b minus a equals f prime of c. In the conclusion of the mean value theorem for the function f of x equals x squared plus 5x plus 4 on the interval from 2 to 3. Okay, so this is a mean value theorem question, just testing if you know a lot about it. Basically, what the mean value theorem says is that if your function is continuous and differentiable between any 2 points that you give, if it's differentiable and continuous among all those values, then what you can say is that if you draw a line in between those 2 points, that's what this is doing. And you take its slope, so say m equals, it's a small positive slope, say it's 0.2. That slope has to exist somewhere else on the real curve as a slope of the tangent line of the actual function. So it looks like in this example that I've drawn, it'd be like right here, where it's got the same slope. It looks like it exists at that point. The slope of the tangent line is the same, 0.2. So that's what it's asking. It's testing first to find that point, I guess, in which, well, first off, what we need to do is among this interval, we need to go ahead and plug in 2 and 3 in for B and A and see what we get. And then after we get that, we have to find the point at which f prime of x equals this after we plug all of it in. So that was a lot of explanation. So I say we just, can I erase stuff? There we go. I say we just go ahead and do this. So let's first solve this. Let's go ahead and plug in 2 for A, B, and 3 for B, and x squared plus 5x plus 4 for f of x, and see what we get. So this will be, let's do f of b. So f of 3, that's 3 squared plus 5 times 3 plus 4, minus f of a, same thing but with 2, so 2 squared plus 5 times 2 plus 4, all over b minus a, that's 3 minus 2. So that's going to equal, well, on the bottom it's just going to be divided by 1. So we only have to worry about the top. That's going to be 9 plus 15, that's 24 plus 28. So that's going to be 28 minus, then we've got 4 plus 10, that is 14, plus 4 is 18, that equals 10. So what this 10 means is that if we have our function, I know, well, it's a parabola, so maybe it looks like this, but between the 2 points that we took, 2 and 3, if we draw a line between that, the slope is going to be 10. So now what we're asked to do is find that one point C where its slope of the tangent line is also 10. So in order to do that, we just set f prime of x equal to 10 and then solve for x. So let's do that. We replace f prime of x with the first derivative of f. That is going to be 2x plus 5 equals 10. And now we solve for x. So we subtract 5 from both sides. We get 2x equals 5. Divide both sides by 2. We get x equals 5 halves. Answer choice C. Question 10. A certain function f of x has the following first and second derivatives. We have got f prime of x and f double prime of x. We're asked how many relative maxima does the original f of x have? Cool, so relative maxima, those are just, if we have an example function like this, we have an absolute maximum up here. That is the largest output that the function ever reaches, but we have 2 relative maxima at the 2 different humps that this function has. So in order to find relative maxima, we need to find f of x's critical points. And to find those, we take f prime of x and set it equal to 0, and then just solve for x. And fortunately, we're already given f prime of x. It's 3x to the 5th minus 6x cubed. So don't even have to find that derivative. We just plug it in. So 3x to the 5th minus 6x cubed equals 0. So now solving for x, looks like we can divide everything by 3, and we'll get 0 equals x to the 5th minus 2x cubed. And then after this, it looks like we can take an x cubed out of both of the terms on the right. We'll get 0 equals x cubed times x squared minus 2. Now we can go ahead and split this off into two different equations. Looks like we'll have x cubed equals 0 and x squared minus 2 equals 0. We'll just solve each of them independently. On the left, we'll have x equals 0. And on the right, we can add 2 on both sides. X squared equals 2. And then square root both sides, so you get x equals plus and minus square root of 2. So there we go. We've got 3 critical points. So we have a potential maximum of 3 relative maxima. So we can rule out answer choice E. But to actually find those, we need to go ahead and set up that chart, that table. But it's a bit different because we aren't given f of x and we don't know what it is, especially because doing the integral, we'd introduce a plus c, and then it'd be even more ambiguous. So we don't actually know what f of x is. So we can sort of adapt this by using f prime of x instead. And I'll show you how we can still get the right answer from this. So we still set it up like normal. We list all of our critical points in ascending order. So we've got 0 in the middle, and then negative root 2 and positive root 2 on either side. But for this adapted problem, let's go ahead and plug in some intermediary values that are in between each of these 3 critical points. So some values that we could use, usually you want to pick values that are easy to evaluate f prime of x at. I guess some easy ones would just be like -2, -1, 1, and 2. Those don't seem too hard. And then we can go ahead and evaluate all of these. But fortunately, it's not as much work as it seems. We don't actually have to evaluate 7 f prime of x's because we're already given 3 of them. We already figured out that these all equal 0. So we can just go ahead and fill in 0 for those 3. And now we only have to do 4 of them. So f prime of -2, that's going to be 3 times. Okay, so -2 to the 5th is 2, 4, 8, 16, 32. -32 times 3 is -96. And then -2 cubed is -8 times 6 is 48. So plus 48, that equals -48. Boom. Now f prime of -1, that equals -3 plus 6. That equals +3. Cool. F prime of +1, that is 3 minus 6, that equals -3. And then I'm going to guess f prime of 2 is going to be +48, but let's go ahead and figure that out anyways. So 2 to the 5th is 32, and then times 3 is 96, and then 2 cubed is 8, times 6 is 48, so -48, that equals +48. Look at that. All right, so now that we have all of these values, what do they even mean? So let's go ahead and think about what this is actually saying. We've gone ahead and computed a bunch of values for f prime of x. And if we look at triplets of them, where the middle is one of those critical points, we can kind of notice something. So it looks like in the middle, we've got our critical point, which is 0. That makes sense. Critical points are just the values where the slope is 0. So that's all right. But what about the 2 points that are on the outside of it? We've got +3 and -3. Well, since the slope on the left is positive and the slope on the right is negative, that means that middle critical point is a relative maxima, since it starts out with a positive slope, hits the critical point, and then has a negative slope. So in this case, in this example triplet that I've just circled, we have one of our relative maxima. And actually, it's our only relative maxima, because if you look at the other 2 triplets, they go the other way around. They're relative minima. It starts out with a negative slope and then ends with a positive slope. That looks like that. So in this case, we've only got one relative minima, one critical point that is a, no, I mixed that up. We only have one relative maxima, one critical point that becomes a relative maxima. So our answer choice is B. Question 11. For some reason on this question, they just have omit question on the answer choices. And I think the reason for that is that this problem is very easy because you can just plug in pi in for this limit and it won't be dividing by 0 or anything. You've got an actual answer, but that answer is not among these 5 answer choices. So what I still want to do this problem, and I think what they meant to do here is they meant to have a minus pi squared on the bottom. That is very similar to a question that I've already done on a previous exam, and when you do that, it becomes a more typical limit problem, where if you just plug in pi, you'll get dividing by 0 on the bottom, and that's usually how these limits go. So I'm actually going to solve this problem instead, just so you guys have a little bit more practice. But for this problem, there basically is no answer choice, and I have no idea how I'm going to explain it when I go to upload this on the site. But anyways, so I think this is just going to be a L'Hopital's rule problem, especially because this is a fraction, and usually these fractional limits are L'Hopital's rule ready. So just to show that, if we go ahead and plug in pi, we'll get cosine of 3 pi minus 1 all over pi squared minus pi squared. On the top, we have, so cosine of 3 pi is the same as cosine of pi, and cosine of pi is -1, which is -1 minus 1, which is -2. Okay, there are so many things messed up with this problem. I think they wanted this top part to be a 0, like maybe if this was a plus, and then this would become a 0. So we'd have 0, and on the bottom we would also have 0 because it's pi squared minus pi squared. This is an indeterminate form, 0 over 0. So because we have that, we can do L'Hopital's rule, which states that we can just take the derivatives of both the top and the bottom, and our limit won't change. And usually after you do that, you can go ahead and plug in your value that x is approaching, and you'll get an actual answer. So doing that to this very modified limit, we get, let's see, on the top we'll have derivative of cosine of 3x. So that's going to be negative sine of 3x. And then we have to do chain rule. We got to multiply by the derivative of 3x. That's just going to be 3. And then this plus 1 becomes 0 because derivatives of constants are 0. And on the bottom, derivative of x squared is 2x. And then pi squared becomes 0. So we've got our new limit here, -3 sine of 3x all over 2x. And now when we go ahead and plug in pi, we get -3 times sine of 3 pi over 2 times pi. Now this equals sine of 3 pi is the same as sine of pi, and sine of pi is 0. So on the top we've got 0, and on the bottom we've got 2 pi. And this just equals 0. So I think the answer choice they wanted was B, but they messed up so many things in writing the problem that ended up being just bogus anyways. But in the example problem that I gave, where this is a plus and there's a minus pi squared on the bottom, the answer choice would be B. Question 12. This is one of these related rates, minimizing, maximizing material problems. A box with a square base and an open top must have a volume of 4 cubic meters. Find the height of the box that has the smallest possible surface area. Okay, let's draw this out. So we have a box with a square base and an open top. So we've got, let's make it a little bigger, like that. It has a square base, which means both of these are the same length, and an open top, and we've also got a height of the box. Cool. So we need to find the height of the box that has the smallest possible surface area. So we need to find, I don't think we need to find what the surface area is, but we need to find the height of the box that makes the surface area what it is, what it needs to be in order to be minimized. But the cool thing about this problem is it has a really easy cheat. So for these types of box with a square base and an open top questions, first you write out your volume equation where you multiply each side length, and then that's the volume. So this is going to be x squared times h. Every single time for these box problems, h is always going to be 1/2 of one of the base lengths. So h is going to be 1/2 times x. So knowing that, we need to substitute that in. So 4 equals x squared times 1/2 times x. And now we've only got one variable to worry about. So we can just go ahead and solve for x, the base length, and then solve for h after that. So we've got, we can multiply the x through and then multiply 2. So this is going to be 8 equals x cubed. Cubed root both sides, we get x equals 2. So the base length must be 2, and since we've said that the height must be 1/2 of 2, that means the height must be 1. Answer choice D. And this is actually true. That is the answer. And there's another type of problem that is pretty similar to it. It's just in a two-dimensional example. I've seen it expressed as like you have a river with, I don't know, fish in the river, and you have a fence along the river where you've got these two side lengths are the same and a parallel side length at the other end. In this type of problem, it's the exact same. The minimum amount of surface area is going to be when y is 2 times the other length. I guess it's kind of the opposite since it's 2 times instead of 1/2 times, but it's still kind of the same thing. It's going to be, I guess, double what the other side length is. So that's a pretty easy way to figure out these box with a square base and an open top questions.